Okay, off we go. Real quick, so don't forget about the attendance quiz, attendance code, clock's ticking. You probably have about a little over a minute and a half left. And back into the math. So here's what we were doing. We were talking about vector fields. It's a new mathematical object, right? It's, I suppose it's technically not new in the sense that it's a function, right? It's a function from Rn to Rn. But the big idea, remember, is that you think of the input point as a point in Rn, and then you think of the output also Rn, but you think of what comes out as not being a point. You think of it as being a vector that we typically imagine having its tail at the input point where you've evaluated. So it's this kind of a construction here. Why would we care about such a thing? I'm going to give you some physical, real-world examples in a few minutes, but again, I think the picture kind of screams fluid flows, right? I mean, if you were going to try to draw just, artistically, forget about math. If you're just going to try to conjure with a pen, what does it look like when a fluid's flowing? I think you'd probably draw something kind of like this, right? So, anyway, that's a good first metaphor for this. Let's see. Another thing I want to mention, and I think this is really important. I think this is the kind of thing it's easy to lose track of. Y'all heard me say ad nauseum that you've got to distinguish in your minds the calculus of graphs from the calculus of level sets, from the calculus of parameterizations, blah, 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 right? And we rattled off several different, let's go ahead and do it again. So when we draw pictures of functions, we've got graphs, we've got level sets. When we talk about a parametric curve, what we're actually drawing is the image of that parameterization. Then there's my sort of, I don't want to say favorite, but I think arguably a most natural example is what I call the literal picture of the function, where you draw both the domain and the target, right? Well, that's four. Four different kinds of pictures that we draw that are totally like different constructions and therefore have completely different calculus interpretations. And then what have we here? Number 5. Right? This is not a graph. It's not a level set. It's not a go through the list, right? This is a completely different type of a picture. So we are eventually, chapters 6 and 7, going to talk about the calculus of vector fields. And what are the relevant things that you can write down that involve derivatives, and what do they represent? What do they look like on the picture? I'm gonna give you a quick glimpse later today of some examples of that. But anyway, for the moment, what to focus on is this is a brand new kind of a picture, and much to say about how useful it is. Okay, let's see a couple of examples. This first example I think is pretty easy. Notice that for any point x comma y, and this works at any point x comma y, wherever you might happen to be, the field vector, notice the formula for the field vector, very convenient formula, it's constant. It's always the same. It's always 2 comma 1. Now how do we draw that? Well, remember our rule. We always draw the field vector for any given point as a vector with its tail at said point. So, this is how we draw that then. Right? So there's our first example. We've constructed a picture of a vector field. And a quick little side note, notice, hey, wait a minute, I thought constants were supposed to be horizontal or something. Right? No, that's for graphs. Right? And again, you got to make sure you don't accidentally conflate different kinds of pictures. This is not a graph, so there's no reason we would expect anything to be horizontal in any real sense just because we've got a constant. Okay. All right, here's another one. Let's look at, here we have a formula that says for any given point x comma y, let's take maybe that point right there. Here's our formula for our field vector. Our field vector, here, let me changed my mind. Let me do it back sort of over here where we have a little bit more room to move. For that point there, our field vector, also x comma y. Okay, wait a second. That's confusing. How am I supposed to make sense out of x comma y? Well, keep in mind, x comma y as the input point. Points have position vectors. Right? So let's first imagine what is the position vector for this point. This that I've drawn there is also x comma y. It's just x comma y thought of now as a vector instead of a point. That is the vector that is our field vector. It's just that when we draw the field vector, again, we draw it, same vector, we just draw that field vector with its tail at the point, not at the origin. When you're drawing a vector field, the tail is at the point. How we doing? Yes?
So, how come it's kind of more for that one, but how come is it just the initial point, how it would get to 2, 1? Why would it, once it gets past 2, 1 on the graph, it start going backwards?
I'm sorry, what?
Sorry, it's kind of hard to explain.
Yeah, so what we have, you may be conflating pictures as a possibility, I'm not sure. But you got to keep in mind, when we say f of x comma y is 2, 1, what I mean is for any point, the associated vector that you draw at that point, this is the vector, and so I've drawn 2, 1 as a vector located with its tail at that.
Okay.
Is that cool?
Yes.
Okay, yeah. It's so easy to kind of get into graph mindset or what have you. Yeah, totally. Okay, so point thought of as a position vector. Oddly, weirdly, conveniently, the field vector is the same as the position vector, and so we draw it as a field vector. And by the way, now the position vector has served its purpose. We typically wouldn't leave that drawn. So here's our picture at any given point. There's our field vector. And notice, always radially outward, and always with a magnitude that is the distance to the origin. And if you draw that sort of, the whole thing, if you draw that everywhere, at every point in the domain, you start, following that rule, always radially outward, always with a magnitude equal to the distance to the origin, you get this picture right here. Yeah.
What is the magnitude of each vector?
Magnitude means the length of the arrow that we draw. Yeah.
Right. So, what would it be for a point like 1, 2? Example.
You mean this 2, 1?
No. I mean for our example where the vector field is equal to x comma y.
Oh yeah. Okay. Well, so at the point at a at a point 1, 2, let's say that's 1, 2.
Yeah.
Well, it says right here that our field vector, this is how we draw it. It's always radially outward, and
it's a square root of 5. Okay.
Yeah. Okay. Yes.
I was just curious, in 3.2 and 3.3, we've been using capital F.
Yes.
Is there any reason for that?
Arbitrary convention. Don't look too deep. It doesn't mean much. Yeah, it's just arbitrary.
Does the F with the arrow that indicate vector field?
Absolutely. So, and we don't always do it. That's the confusing thing. So sometimes we have vector valued functions. Like if you think about, for example, our change of coordinate formulas for polar coordinates, the output is vector valued, but we don't draw the little arrow over it. And there's no particularly good reason for that, right? The convention, perhaps odd convention, but the odd convention is that when you're talking about a vector field, you do draw the little arrow, but it's not universal and it's not required. It's just I'd say it's routine, but yeah. Right. Okay, here's another one. This one's a little trickier, but this is a really nice exercise. I'm going to talk through about half of this example and leave y'all to do the other half. Let's see here. For a given point, x comma y, let's say arbitrarily here. Now keep in mind, that's x comma y viewed as a point. Points have position vectors. Let me draw the position vector. I claim that if you take a quarter turn counterclockwise of that position vector, Now let's draw a picture. I mean, here's our position vector. A quarter turn counterclockwise would kind of sort of do like this. And the result of a quarter turn counterclockwise would be a vector like so. And I claim, good exercise for y'all to fill in the blanks home, if you write down the formula for a quarter turn counterclockwise, remember, rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns, blah, blah, blah. All right, all that linear algebra stuff. Go through, play that game, write down that matrix, apply it to x comma y. What you will find you get is that field vector minus y comma x. So now, of course, we don't draw field vectors with their tail at the origin. We draw field vectors with their tail at the point where we're evaluating the field. So we draw it like that, right? And this is just that was just kind of a guide to help us think through what was going on. But so we get this resulting picture of what this vector field looks like. And ultimately the point is what I have in blue here, that the quarter turn rotation matrix is what allows you to make that connection. So fill in those blanks. Again, I think it's a really great exercise. Write down the matrix for this rotation. Note that when you rotate xy, you get minus yx. And then we conclude this picture. Okay, as always, if you get stuck, if you're not sure, if you're confused on where to start, whatever, come talk to me in office hours. I'm very happy to help. Okay, here's some more examples. This is a really big one in physics. Y'all are mostly engineers. I know you're not all, but mostly engineers. This is a really big deal in physics and engineering. Right? Anything that's a big deal in physics has got to be at least a bit of a big deal in engineering. So this is called an inverse square radial inverse square vector field. It doesn't look particularly familiar when you write it like this. You see this cube in the denominator, right? But I think it's very helpful algebra to do the following. Notice that this is a unit vector that points radially outward. And then notice that the magnitude is inverse square. Right, so that's why they call this radial inverse square, even though there's a cube in the denominator. The magnitude goes as the inverse square. So what? Well, if you think, flashbacks to high school physics, right? What's the formula for gravity? Well, it's radial inverse square. They don't say it like that, but it's always, toward the origin, or if the origin is where the mass is, right? And the magnitude of the gravitational force is the reciprocal of the square of the distance. So it's radial inverse square. And then likewise, think back, I don't know if you had an E&M course in high school, or maybe you've already had one at Duke, but electric forces are also radial inverse square. Right? So this is a really big deal. This vector field comes up a lot. It's very, very important. And there's other really cool things about it that I won't reveal just yet. Okay. All right. So heads up for that. Oh, by the way, notice the picture that I drew here is inward. When I drew this picture inward instead of outward, I was thinking in terms of gravitational fields, which of course are inward. Thank God. Right? Can you imagine if gravity was outward? We wouldn't be here. Right? Anyway, all the why inward, not outward, it just means that this C is negative. So C can be either positive or negative. Okay, here's another one. Let me bore y'all for a second. We've already studied gradients. We already know that they point uphill. Specifically, they point uphill on the graph. Old news, right? We've already talked about that. The way we phrased it at the time was that gradients point in the direction of steepest ascent. And then again, I quibble with the language. I like to call it the direction of fastest increase, et cetera, et cetera. But if you're looking at a graph, direction of steepest ascent makes good sense. It's a natural terminology. And it's just a fancy way of saying it points uphill. So again, old news. Nothing new there. The observation I'm going to make is just that, hey, check it out. When you write down the formula for the gradient, there's the formula for this particular function. The gradient is a function. You plug in different points, you get different vectors. Oh my gosh, that's what a vector field is. Right, so we didn't think of it this way at the time, but the gradient is a vector field. When we were talking about gradients before, we were thinking about one point at a time. We were focused on, okay, here we are, we're at one point, and I just want to know what's happening in the general vicinity of that one point, so we thought of the gradient as a single vector. But you can talk about the gradient anywhere. It's a vector field. All right. Now, a little bit of terminology to talk about. I'm going to tell you what I think the natural terminology should be first. And that is, keep in mind, gradient. What gradient does is it takes a multivariable function and it produces from that a vector field. And I think it's pretty reasonable that thing that comes out of the gradient operator, we should call the gradient because that's how we computed it. It's the gradient. So let's call it the gradient. Isn't that extremely natural? Right? When you take a derivative of something, you call it the derivative. Well, of course you do. Right? So now let's talk about if you go the other way. If you have a vector field, and if you ask, what is the function which, if I were to take the gradient, would give me my given vector field, I'm going to borrow from single variable calculus. I'm going to suggest we should call that the anti-gradient. I mean, if we were thinking about derivatives again, we would call this the antiderivative, right? So I think anti-gradient makes loads of sense. Precedent and structurally natural, that you're going backwards, it really makes sense. Okay, so that's my favorite terminology there. FYI, the more common terminology is to call this function the potential function. So heads up, you're going to hear that term a lot. Now, why do they call it a potential? What's the motivation for calling it a potential function? Well, the idea, and this is totally true, there is this idea of a force, and sometimes, not always, importantly, not always, but sometimes the force is the gradient of something. And that something, the thing, whose gradient gives you the force, very closely connected to potential energy. Right? So you can see it's nothing weird about this, that the thing that is commonly called the potential function, very closely connected to potential energy. So a case can be made. That's also pretty natural terminology. And I get that. Here's the problem. It isn't potential energy. It's the negative of potential energy. And to me, that's confusing. We're describing something with terminology motivated by not the thing, but the negative of the thing. I think that's weird. By the way, why is it the negative? Easy example, let's think about gravity. Right, y'all know about gravity, right? And you don't know about gravitational potential energy. Potential energy goes higher the higher you go. The formula for potential energy is some constant times z, right? Okay. The gradient, therefore, points up. The force points down. This is a constant annoyance. The gradient actually points opposite of the direction of the force, depending on how you define things. So that minus sign is what it is. So I recognize that this is the more common term, but I'm going to put a frowny face next to it because it's not potential energy, it's the negative of potential energy, and that bugs me. The other reason I don't like that term, I'm going to give it a second frowny face, is because we're not always talking about potential energy. sometimes we're doing math for whatever other reason, and there is no force involved in the story, and there might be, therefore, no potential energy involved in the story. Why would I use a terminology motivated by a physical scenario that it's not relevant to what I'm doing? So I would criticize this as being a narrowly motivated term. It only makes sense as terminology if you're talking about potential energy and gradients relating to forces, which is not all of what we do. Okay, but nevertheless, very common term. Be on the lookout. Pause. Questions? I'm moving pretty fast, but that's the nature of the course. Everybody doing all right? Okay, moving along. So let's talk about some physical examples. We've already talked about gravity. We've talked about electric fields. In both of those cases, the vector fields represent forces. I claim vector fields don't always represent forces. Here's a bunch of examples of vector fields that are not forces. Right? So in 2 dimensions, right, we can talk about airflow. Anytime there's a hurricane, you can go to the storm apps or whatever, storm tracker apps, and they have little pictures that show the arrows, right, representing what the wind direction and wind velocity is at wherever you might be looking on the map. They're literally drawing a vector field representing airflows. Right? So it's pretty relatable, I think. And pretty much any other flow of a fluid, right? So ocean currents, how pollution is moving around within the atmosphere or whatever, or on the surface of the earth, either way, blah, blah, blah. So there's some two-dimensional examples that I think make sense. My favorite one, this is just kind of fun. I'll point out that animal migrations you can think of as vector fields. In particular, you can think of animal migrations as a flow of a fluid. And I know, animals are not fluids. But you know what? Are we sure about that? Maybe they are. Maybe large groups of animals are fluids. By the way, what's the classic fluid, what everybody thinks of as being a fluid? Water? What's water made up out of? It's a bunch of teeny tiny little things. Molecules. Right? They're little discrete objects. Right? So if we are talking about the migration of, 5 million birds, that's a whole bunch of, at least on the scale of what we're talking about, teeny tiny itty bitty little things. They're kind of a fluid. Does that make sense to everybody? I think it's a nice point of view. So you can absolutely think of them in that sense. Et cetera, et cetera. Okay, so 2 different ways to think about vector fields, or what I call 2 different metaphors for vector fields. Vector fields, you can think of them in terms of forces. You can also think of them in terms of fluid flows. Okay, now there's a really important calculation that we need to do here. It is going to come to us as just a question, and the answer is going to be an expression that we're going to do a lot with. But for the moment, let's just think about this as a question. So I've got a vector field. It represents the flow of the fluid in the sense that the field vector is the velocity of the fluid, wherever you might happen to be. The field vector is the velocity of the fluid at that point. Let's just say. And now, so there's our field vector, by the way. Let's consider a small flat area like this. Some small flat area. I've drawn it, by the way, as being a parallelogram. It doesn't have to be, but it's going to make the computation a little easier, so let's just do it like that. And by the way, we're going to need to talk about how that piece of area is oriented in space. So I'm going to talk about the unit normal vector. So this is a unit vector that's perpendicular. Right, so if my hand is the piece of surface, right, then my stylus here, you see how it's perpendicular to my hand. If I know what direction that normal vector is pointing, then that helps me understand how that piece of area is sitting in space. Does that make sense? Everybody's happy? Yeah.
So it's perpendicular to the plane, not the field.
Correct. Yeah, perpendicular to the surface. That's right. That's right. So this is the normal vector for the surface. Flat. Small, flat surface. So what I'm going to want to do now is let's ask, what is the flow rate? Try to get this all on the screen. What is the flow rate? What is the volume per unit time that's passing through that surface? And again, just, reminder, we've got this surface, the surface sitting here. There is a fluid flowing. Some of that fluid is literally going through the surface. I would like to know, volume per unit time, how much fluid is flowing through that surface. Perfectly natural question to ask. Right? All right, so how are we going to do that? Well, what I'm going to do is I'm going to entertain some amount of time, delta t. Let's just start the stopwatch and then stop the stopwatch, just a fraction of a second later. Notice, if this is your velocity, then in some time delta t, you will have the fluid will have flowed some amount in some direction. We're going to call that the d vector, d for displacement. That's how much the velocity, that's how much the fluid has displaced in that amount of time. And then I claim, I think this is pretty believable, that this right here, this is the volume of fluid. That in green, that's the volume of fluid that has flowed through that surface in that amount of time, delta t. So let's compute that volume of fluid. Let's see here. So that volume, well, first of all, okay, I've got a kind of a lot going on here. Let me clean up the mess. The volume of fluid, I propose, is going to be the height. Do a better artistic job there. It's going to be that height times the area, which I think I did in yellow. Right, y'all remember your high school geometry? Oh yeah.
What is D?
What is what now?
D.
D is the amount of displacement. So in some small amount of time, delta t, the fluid moving with this velocity, right, field vector is velocity. Well, in that amount of time, moving with that velocity, the fluid that started here will have ended up here. This is how far each little piece of fluid has flowed. Yep.
I'm not totally sure that the total change in the volume of fluid is equal to the volume of that shape that you drew.
Yeah, it's a physical appeal. I mean, so a piece of fluid that was here, displacing by this amount, will end up here inside of this thing, and it flowed through the surface. And any piece of fluid that has flowed through the surface, let's see how to say this. Everything, if you look at any point in this parallelepiped, thank you, and you say, okay, where was it delta t seconds ago? Well, you keep in mind that this was the displacement. Anything that's in this parallelepiped, you go backwards by d, and you will have passed through the surface.
Yeah.
Yeah.
But don't you only care about that one point r, not necessarily...
No. I'm interested in the fluid that's flowing through the surface. Forget about R. R is irrelevant.
Is that why it has to be small?
Yeah. And for our purposes here, everything is flat and constant and as simple as possible. So don't worry about a non-constant vector field. We'll deal with that later. I just, small, flat, constant vector field.
So it's FR everywhere.
Yeah, that's right. F of R is, for our purposes here, is constant. Yeah, absolutely. Okay. All right. So, so height times area gives me volume. Again, flashback to geometry class. That height, I propose, is the normal component of the displacement vector. Now, again, geometric appeal, right? This got this displacement vector. I don't really care how long the displacement vector is exactly. What I care about is to what extent does that displacement move in the direction of the normal. That is how we define the height. And of course, we know how to compute components. Components are dot products with unit vectors. Conveniently, n is a unit vector. And then, by the way, what was this d vector again? Let me, again, do like so. The d represents, well, how far did the fluid moving with velocity f displace in an amount of time, delta t, and displacement is velocity times time. Now, there's a lot of little, the nitty-gritty little details in here, and don't get lost in the details. You got to think about the details, yeah. But big picture, we're just looking at volume per unit time and computing. And we have a nice punchline, and that is our flow rate that we're interested in, volume per unit time, keeping in mind that there's the volume, and you see it's proportional to time. The volume per unit time is this right here. And so, as is often the case when you're doing math, and when you ask a reasonable and natural question, the answer to that reasonable and natural question is an interesting thing. And this one turns out to be interesting enough that it's deserving of having a name and a notation. This is called flux. We represent it with a capital Greek letter phi. Kind of like the spherical coordinate phi, except capital and still lowercase. So it's got the serifs. Is this called serifs, I think? Anyway. So there you go, flux. Alrighty, now there is a closely related calculation that I'm going to get you all to do for yourselves. This is a nice exercise. Okay, if you want to make sure that you understand what we did here. By the way, step one, make sure you understand what we did here. Right? Think through the details. Make sure you're comfortable with everything that happened in the calculation. And then we're going to modify the question. The calculation gets modified accordingly. Now let's ask the question, suppose your field vector no longer represents velocity. New scenario, suppose your field vector is, this is going to seem weird, but fluid density times velocity. What an odd choice. Why would we, velocity, you get why velocity would make sense, because that's something you can see, that's what the fluid is doing. Why would we multiply by the density? Granted. Reasonable question. I'll give you the answer in 10 seconds. The reason is that if you ask this next natural question, not volume per unit time, but what is the mass per unit time of fluid? Now again, natural, reasonable question. If you've got a fluid, maybe I don't care about how many cubic feet of fluid it is. Maybe I care about how much does it weigh? Or if we're talking about birds migrating, I don't really care about the volume of birds. I care about the number of birds. Right? So reasonable question, quantity, not volume. It turns out the answer is again flux. It's the exact same expression. And you might say, hey, wait a minute, how can you get the same answer to a different question? Well, keep in mind, it's not quite the same answer because this field vector no longer represents velocity. Now this field vector represents density times velocity. So the way you're going to do this, and again, this is a fabulous little exercise. You're going to start totally analogously to what we did here. Here we wanted volume per unit time, so we started off computing volume. Here we want mass per unit time. You're going to start off by computing mass. which of course is density times velocity. So you're just going to tack on a factor of density. It carries through, and then what happens at the end? It just absorbs back into the field F at the end. So anyway, details, excellent exercise. I encourage you to think through those details. Again, as always, come talk to me in office hours if you get a little stuck or something. No problem. Happy to help. It's a great little exercise. The punchline is flux is a useful thing, and it's an answer to reasonable natural questions. You might want to know volume per unit time, in which case, if you want to know volume per unit time, just let the vector field represent velocity, and boom, flux will do it for you. And then likewise, by the way, sometimes you might want to know mass per unit time of fluid flowing. Okay, well, all you got to do is make sure that your field represents density times velocity, and flux will do it for you. Very, very useful construction. Okay, I am sad about the fact that I don't get to talk about this page. This is a really, really cool page. A lot of wonderful ideas here. One of the things that I get excited about, and I think most mathematicians do, is when there are subtle ideas that can turn a really hard problem overwhelmingly, seemingly, how could we even possibly get our hands on this, into actually a pretty straightforward, simple calculation. And that is what happens on this page. And tragically, we don't quite have time for it. It's a bit of a digression, and so you're not responsible for what's on this page, but y'all will have engineering lives, and y'all will sometimes encounter the following situation. And the situation is you might have a weird fluid, such as the flow of light. Let me use brighter colors here. Let's see, I'll use orange. That feels like a light bulb. And yellow just doesn't show up very well. Okay, I'll use green. I guess that's good enough. So suppose you have two light bulbs. Well, light bulbs emit photons. They kind of behave like a fluid. Kind of, sort of. Right? They're little things kind of all flowing around. That's what fluids do. The problem with this situation is that if you ask at a given point what is the velocity or what is the density times what have you, the problem is you've got some photons going that way and you've got some photons going that way. So like which direction, if I'm going to associate a vector to this point, which direction even should it point? It's not clear how I would define a vector field to represent this flow of this kind of a fluid, right? So the answer is that you kind of take what we have on the previous page and just turn it around backwards. I guess I wish we had more time to go into details, and I have a super cool example to follow that we can't do. On the previous page, the premise was that we know the vector field, and we're trying to figure out the flow rate. Well, what we're going to do now is we're going to presume that empirically, perhaps, we know flow rates. Right? You could imagine having actual pieces of surface oriented in some actual way, and that you were actually measuring flow rates and how much fluid is flowing through the thing. And then you could ask, very reasonably, okay, what vector field would make this equation work? And it turns out in the case of two light bulbs, this is perfectly doable. It makes great sense. It totally works. And even in cases where you have many point sources, possibly even more than point sources, maybe you have like this example down here. We have a ball of glowing gas, and every single point inside the solid is its own separate light source. Right? Infinitely many light sources in this approach totally works, and you get some really awesome results. And we can't spend time on it. Anyway, big idea though that turning this equation around the other way is a foot in the door. Okay. Last idea in this section. This is really actually a pretty straightforward idea. Keep in mind that sometimes our vector fields represent velocities, and sometimes that fluid that's flowing around, you might imagine that some particle, it just gets dropped into the fluid, some little massless, negligible mass anyway. By the way, I like to think about the surface of a river or a creek or whatever. There's water flowing on the surface of the creek. And, it's fall, right? We're literally at fall. Imagine a leaf falls into the river. What does it do? Does it sit there and fight the current? No, it goes downstream. The leaf goes exactly where the water tells it to go. Right? It follows the current. Does that make sense? Physically? All right. Well, let's just think it through. If I'm interested in the particle, well, the velocity of the particle, I hope this isn't a surprise, but the velocity of the particle is going to be the same as the velocity of the fluid. Leaves do what the water tells it to do. If the water is going that way, well, that leaf is going to do exactly the same thing. What do you think? Yes?
What if, so it just depends where it lands?
Yeah, that's right.
Like water is, as I said, a bunch of tiny particles. What if, the particles that land on are in two different directions?
Yeah, that's a great question. Fabulous question. And water, thankfully, doesn't do that. Water can't, photons have this nice feature that they can pass through each other. And water particles can't do that. So if you have two flows of water that kind of from different directions hit the same point, they'll have to figure out some way to go together. Yeah. So when you have water moving through at any given point in a river, at that point, the velocity of the water at that moment is a single vector. Yeah, it has to be. Yeah, that's physical. That's just the way of the world. Yeah. Okay, so so if you've got a particle, the velocity of the particle is the same as the velocity of the fluid. Particles do what fluids tell them to do. By the way, velocity of the fluid where? Well, the particle is influenced by the water where the particle is, right? If you drop a leaf into the river, and I say that the flow of the water is what makes the leaf move, well, it's the flow of the water where the leaf is. Now, I don't care what the current is over there. That's irrelevant, right? It's at the point where the leaf is. So we get this equation right here that I will circle in green, and then let me remind you that the velocity of the fluid is what the vector field is. And so all of that together gives us this equation. This is a system of differential equations. Y'all probably haven't seen how to solve systems of differential equations yet, but you will in Math 353. Conceivably, if you took Math 221, you might have seen something like this. If you haven't, don't worry about it. In this class, we're not going to talk about how to solve these kinds of differential equations. But it turns out that there's techniques. So what we are going to do is confirm certain solutions. And for example, if you were to imagine, let's see here, as the vector field, this right here, and keep in mind we've seen this vector field before, right? This vector field, that's the one where it's sort of rotating counterclockwise. I could totally imagine a fluid doing that, right? This is what I like to call the stirred pot. If you have a pot of water, you're making pasta, whatever, right? You got a pot of water. If you stir that water, the water will start flowing exactly like this. And then you can say, all right, well, if I drop a oregano leaf, right, onto that oregano leaf is going to go around in a circle, isn't it? Right? And y'all can confirm this for yourselves, that this what I've written as x of t, I should probably call that r of t. I think this was just an oversight. I think I mentioned before, I used to call x comma y by x of t, and now I'm switching to the more standard convention to call it r of t, and I think I just forgot to change this one. Think of this as r of t. We plug in this parameterization into this system of differential equations where f is this vector field, and you can just confirm the equation works. Yes?
So basically the new equation would be negative cosine of t and then sine of t inside the...
It would be negative sine of t, because y is sine of... Yeah. Right.
Okay.
Yeah, so effectively you're confirming that the derivative of cosine is negative sine and the derivative of sine is cosine. Yeah. Right. Anyway, you plug in that parameterization and the differential equation works. So again, good exercise. I think there's one homework exercise where you'll pretty much do exactly that. Heads up, here's something I've noticed over the years. Students taking this class have some, I don't want to paint with too broad a brush, but some students taking this class decide right along in here that they like one of these metaphors better than the other. Some people decide, you know what, I like forces, I understand forces, this fluids thing, it's weird, I've never thought about fluids, I'm just going to think of everything in terms of forces. Yeah, that doesn't work. There are some things that we're going to do, there's some math that we're going to do that does not make intuitive sense, that you will not get. You'd be hope if you try to understand certain of the math that we're going to do from the point of view of forces, it's a losing proposition. You have to be able to understand fluids. And then other students will say, you know what, the fluids thing just totally makes sense to me. I think I'm going to just think always in terms of fluids. Yeah, there's other things that we're going to do where you really have to think about it in terms of forces for to get any sort of physical intuition. So, heads up, you do need to be able to interpret vector fields in both of these senses, both the forces point of view and the fluids point of view. Don't just pick one. That will paint you into a corner and you won't be able to get out. Yeah.
So forces would be like gravity and...
Mm-hmm. Yep, absolutely. So yeah, so make sure to try to digest both of these examples. Yes.
Concepts that we just learned, like flow rate or flow line, those are specific to fluids. We don't need to understand those in like a force-based concept.
I think that's a nice example of where the fluids really makes loads more sense than forces. Yeah, absolutely. Right. Okay, moving along. So section 3.4 is a weird one. There's big ideas here. This is where, by the way, this is the glimpse that I'm going to give y'all into the calculus of vector fields that we're going to flesh out much more thoroughly when we get to chapter 6 and 7, right? So this is just a glimpse. This is just a planting of thought. And we'll let that kind of, stew for a month, or let's see here, what is this, October, November, month and a half or so, right? And then we'll come back and we'll be much more thorough later. So anyway, here we go. The idea, y'all have seen gradient before. First idea I'm going to throw at you is that you can think of gradient as being this, what I'm going to call operator, being applied to a function f. Now, okay, whatever, right? But I mean, the idea that we would think of a differential operator by itself, kind of a weird thought, right? But if you do, this thing here, this differential operator, a vector where the coordinates are just the partial operators themselves, that if you apply it to a function f, you would actually get gradient. It's just kind of what it would look like when you smash that into that. So I hope that seems like a reasonable thing. And this is part of how we define this thing called divergence. So much to say about divergence. what does it look like is the very first tip of the iceberg question. But it turns out divergence is the right answer to a great many questions. But again, that's all chapter 6 and 7. That's future. We'll get to that when we get to that. But the way you compute divergence is you just take the del operator, which of course is just the various partials, and we don't apply it to a scalar, we dot it with a vector field. So I emphasize that's a dot. And when you dot, you apply the coordinates, coordinate-wise, and then add. So this is how you would naturally write that dot product. It's the sum of those individual things. And it turns out that this expression, I've given you zero motivation for this, I emphasize. It turns out, and we'll make good sense out of this later, this expression is massively important. So it's called divergence. It's written as div f, but honestly, it's more commonly written as del dot f because it's so compact and frankly just kind of cool that works out algebraically. Yeah.
I'm just like curious with the notation. So in this case, like that big F with the arrow is like a function.
It's a vector field.
I'm like, oh, okay.
Yeah, it's a vector. So that's right. So it has several output components because vector fields are vector outputs, and each one of the I'll say this: the inputs are x comma y comma z, and so each one of these f1, f2, and f3 is a function of x, y, and z.
So it's mapping from 3 variables to 3 variables.
That is exactly what vector fields do. That's right. Yeah. Okay, so we're out of time, so we will draw the line right here and see y'all on Friday. Have a good one.